So thanks, Renee. And so the first thing to note is that while Bob, Cedric, and I are presenting this, the work which actually went into all of the new rheology features and planned rheology features in Aspect spreads across basically the entire developer group and quite a few users. So that's the first thing to note is the work contained in this presentation includes a much larger group than just the presenters. So thank you to everyone who contributed for this. So in addition to talking about the new and planned features and Aspect, we thought it would be really helpful to discuss a number of other topics, basically as setting the stage. So then first, what is involved in actually simulating tectonic deformation? I'll call it tectonic deformation being all of the solid earth processes we might be interested in. So then what are the current features which are in Aspect to which you can use right off the bat? Then also, what is the material model structure? And we'll go into a little bit about what exactly a material model is. And then finally, we'll go into the new in development and planned features, which many people might be interested in. And so when we think about what tectonic deformation is, I always like to start with this sort of schematic cross-section produced by the USGS as a sort of a classic figure. And the idea here is just illustrating all the different tectonic processes most people here are interested in modeling. So then, for example, one process might be subduction over tens of millions of years. So this is long-term deformation, involves viscoelastic plastic deformation, phase changes, potentially fluid transport. But then you might go all the way up into the continental crust and rift zone, and then you might want to examine fault interaction over seismic timescales. So then the point being a wide range of processes. And so then to start out in thinking about sort of framing tectonic deformation in terms of physical processes we could include in the code, this is my sort of do-it-all list. So then this is a wish list of everything you would want in a code to simulate tectonic processes. So then you might want to track properties for distinct rock types. So for example, distinguishing the crust and the mantle. You might want to include compressible deformation, both elastic and viscous. You'd want phase changes. You want a wide range of different viscous flow types. So this could be diffusion, dislocation, Pyle's creep. You may also want to include grain size evolution in those processes. Elasticity, again, ideally compressible. You'd want brittle failure to simulate faulting. But then when thinking about brittle failure, you might want to start considering dynamic for static, a dynamic for static coefficient of friction, strain dependency, and then also different stabilization schemes for plasticity. You could then think about also how to frame composite rheological formulations, and then getting into the really complex stuff, you might want to start including two-phase flow, magmatism, and fluid rock interactions. And of course, you want all of this to be using thermodynamically consistent approximations if possible. So then before going into what exactly is an Aspect right now, let's think about where this is handled in the code. And this is primarily done in the material models within Aspect. So as many of you probably know, there are many materials in Aspect which do different things. And so some examples of these are the simpler material model, the viscoplastic material model, and the melt global material model. There are quite a few other ones. These are just kind of 3 end-member examples. So what are the primary inputs? So this is not a comprehensive list, but this is kind of the main things you would use or that the material models use. And so the inputs into the material model are temperature, pressure, velocity and strain rate, and then composition. And so then these are basically the variables the code needs to calculate both the thermodynamic properties. And so examples of those would be density and thermal conductivity. There's a few other ones Aspect calculates in the material model section. But then viscosity and composition reaction terms. And so composition and reaction terms could be used to modify, lithologies you're tracking, or could also be used to modify things like elastic stresses or finite strain accumulation. All that's handled through the composition reaction terms. So then that's what goes into the material models, the inputs, and those are the primary outputs. So now then, if we think about this idea of simulating tectonic deformation and what currently exists in Aspect. So what I'm going to summarize here is, so then what most people probably do if you are simulating tectonic deformation, which includes viscoelastic plastic deformation, so deformation of the lithosphere and also deformation of the upper mantle, most people are probably using the viscoplastic material model, although there are quite a few number of other material models which do more specialized things. So for example, there's material models which handle two-phase flow, and there's also a material model called grain size, which handles grain size evolution, which can be used for looking at subduction in some cases. So, but then what is in the viscoplastic material model? And what I'm putting right here next to each of these basically items is a check mark, which means it's implemented in the code. This sort of in progress symbol means it's something we're actively working on, and it may partially be in the code, or it's something which is an employer request. And in this one case for compressible elasticity, it's something we have thought about, but we have not actually started working on. So then right now, on the viscoplastic material model and other material models, you can absolutely track different properties for distinct rock types. You cannot currently do compressible deformation, although we are starting to work on that. Phase changes to some degree are implemented, and how Yen and Magley talked about this yesterday. You can do viscous flow, including diffusion, dislocation, pearls creep, and some form of compositing. Although Bob Myhill and a number of other people are working on more advanced options for compositing, which is going to be discussed later in the talk. Grain size evolution is not yet included, but we're going to be working on that hopefully in the future. Elasticity is included, but it's incompressible, and we have not yet started in any capacity really working on compressible elasticity. Brittle failure is implemented through a Drucker-Prager-Yeo criterion. And dynamic friction, or at least rate state friction, is not yet implemented, although Ann and S are working on this, are going to be talking about that later today. We do have strain dependency for brittle failure, and then also there are some stabilization schemes implemented for the plasticity, which Cedric is going to talk about. Bob is going to talk about the composite rheologic formulations, some of which are already implemented. But then sort of another longer term item is then Jonathan Perry-Houts and Julian Damberg and myself and a few others are working on slowly implementing two-phase flow magmatism and fluid rock interactions into viscoplastic material model, although this is a bit more of a longer term project. And at least right now, the viscoplastic material model, it is thermodynamically consistent with the equation of state sort of structure we are using for it. So then another sort of general point is that if you're an experienced modeler, but you're new to Aspect, how do you get started sort of simulating these complicated tectonic processes? And this would be the order of operations we would suggest. And then first start by reading through the manual. Then you'd want to go through the benchmark folder because there's quite a few benchmarks illustrating different problems there. The next step would be to go through parameter files from published studies. An example of this is the study from Anne published in 2020 looking at rotation of the Victoria block in the East African Rift Zone. And the point here, especially with this, is that now there's quite a few published studies looking at sort of complex tectonic deformation. And although you may not want to do exactly what's done in that study, these parameter files published with the study are an excellent starting point if you want to start, if you don't want to start from square one. And then sort of the last thing we would recommend doing is that if you want to understand how a specific feature works and potentially start implementing new features into the code, at that point, you want to start going through the test folder. And in particular, you can look at the viscoplastic test suite. So then the last thing we wanted to do before I hand this off to Bob is then sort of think about the material model, material model structure. And a number of people have been doing a lot of work over the last year to simplify how the material models work. And so then basically, if you were to go into the source code, and then we can do this after the talk ends, actually do an interactive sort of session looking at how the code is structured. And so then if you were going into the folder source material model, what you would actually see is not just the material models listed, but you would also see two additional folders. And so there's a folder for equation of state modules and rheology modules. And so the idea here is that what we've started to do over time is rather than have everything combined to a single material model, so basically all the functionality you would need contained within a single file, we've started to subdivide it into these modules which contain discrete pieces of code. So for example, in the rheology module section, there's a discrete rheology module and piece of code for diffusion creep, dislocation creep, Parles creep. There is a rheology module for elasticity. There's a rheology module for Drucker-Prager plasticity, and there's a rheology module for strain-dependent behavior. So then why do this? There's a couple of reasons. First and foremost, it's much easier to read, debug, and expand the code with this format. But then the second very important point is it allows users to combine the equation of state or rheology modules in different ways. And so then effectively, if you wanted to create your own new material model that does something slightly different or very different from viscoplastic or another material model, having these modules should make it much easier to do that. And with that, I will hand this over to Bob, who will now talk about the composite rheologies.
Thanks, John. Okay, so John's given a really nice introduction to some of the changes that have been made recently to the material model structure. The previous slide showed a few different rheology modules, and all of those rheology modules have one single deformation mechanism implemented. So things like diffusion creep, dislocation creep, Pearl's creep, those are all single mechanisms. Real earth materials are much more complicated than that, and they have multiple mechanisms all acting potentially at the same time. So it's pretty common that you will have some amount of diffusion creep and some amount of dislocation creep happening at the same time in the same rock. So we really want to have some kind of formulation that can deal with that, and viscoplastic is one of the modules where that's done already. So on the next slide, I want to describe the way in which the viscoplastic material model is implemented. And essentially that assumes that all of the different viscous deformation mechanisms experience the total strain. So you can imagine that there are in fact lots of different rocks all lined up one against each other. And one of them is undergoing dislocation creep, and another one is undergoing dislocation creep, and they're all being deformed at the same total strain rate. That's a perfectly good approximation in some cases, in particular in those cases where all of the viscous deformation mechanisms are only weakly dependent on the strain rate. So you end up getting this harmonic viscosity law where you can add up the inverses of all of the viscosities of the individual flow laws, and that'll equal the inverse of the total effective viscosity. In real materials, it's actually a better approximation to assume that all of the different mechanisms experience the same stress, with strain rate partitioned amongst the different mechanisms. So for example, diffusion creep and dislocation creep, those two deformation mechanisms are implemented in the diffusion dislocation material model in aspect. And instead of using the total strain rate, those assume that each one of the mechanisms sees the same stress, and then the strain rates are partitioned between them. So you end up with a slightly different effective stress and slightly different effective viscosity. So the pros and cons of these two different formulations, the one that's used by viscoplastic and the one that's used by diffusion dislocation, the pro of the viscoplastic formulation is that there's no need to calculate the strain partitioning between different mechanisms. You have the total strain rate for all of your different viscous deformation flow laws, and therefore there's no partitioning that you need to do. And the reason that that is good is that it allows you to evaluate the properties of the material model much faster. The cons are that this formulation tends to over-weaken strain weakening materials, because all of those materials are seeing a larger strain rate than they would actually experience in a real rock, and therefore the stress is overestimated, which tends to decrease the viscosity. Another con is that there's no way to incorporate mechanism-dependent damage. So for example, grain size evolution, we normally assume that grain size changes are due to dislocation creep. So you have to work out the amount of strain rate which is being accommodated by dislocation creep. And of course, you can't do that if you're using the total strain rate for all of your different deformation mechanisms. The final con that I've included in this list is that the viscosities of multi-component materials, so here I mean if your material is made up of lots of different rock types, or if you're looking at a smaller scale and you want to simulate a single rock that has different grains which have very different rheologies, like for example a mica garnet schist, then you can only average those viscosities, assuming that every one of the rocks sees the total strain rate. And I'll come back to that in the last slide. So before I show you a perhaps overcomplicated figure showing the new composite formulation, I wanted to give you a very quick primer on the analog diagram that I'll be showing you in a couple of slides. So if you're not familiar with any of these, essentially all we're doing in these diagrams is we're representing the deformation that's going on in our 3D rock in a simple 1D way. So at the bottom of this slide, you can see 3 different diagrams. So the first one, this is a model of essentially a viscous damper. So the idea is that you impose a stress on the left-hand wall. The right-hand wall is fixed, and that damper will deform according to its viscosity eta. The second diagram, the one in the middle, is essentially just a spring. So here we have stress is proportional to the strain rather than the strain rate for the viscous element. And then the final diagram on the right-hand side, that's a plastic element where the stress increases, where the stress is equal to the total stress until you reach a yield stress. And then that plastic element just accommodates the yield stress, and any additional stress goes into deformation. So moving on to the next slide. These analog diagrams, each individual element can be combined in 2 different ways. Either you can put 2 different elements in parallel with each other, or you can put them in series with each other. And if you put them in parallel with each other, that's essentially saying that both of the elements are seeing the same strain. So that's what we can see in the first diagram on the left. So here we have E.1 equals E.2 equals the total the total strain rate. And essentially what that means is that each component is accommodating part of the total stress, and you basically just add up the 2 stresses to make the total stress. And in terms of viscosity, if we're looking at simple dampers, the effective viscosity is then the sum of the viscosities of each one of the 2 components. On the right-hand side, you can see the isostress composite. So if we're putting the 2 elements now in series with one another, and here you can see that the stress is the same with both elements, and now you're adding up the strain rate from the first component and the second component to get the total strain rate. And this ends up giving us our harmonic viscosity law, which we saw in the previous slide. You can see that this partitioning of the strain rate is what we actually want to do in our single rock materials. And so in the next slide, you'll see what we have planned for the composite rheology model. And this is mostly implemented now, although there are still a couple of pull requests that will need to be merged in the next month or 2 months or so. So here you can see in the top part of that diagram that there are now 5 elements all in series with one another. The first one is a diffusion creep, so this is just a viscous flow law, and then a dislocation creep, and then a Pearl's law creep damper, and those all act in series with one another, so the strain is partitioned amongst them. The next element after that is a damped plastic element. So that plastic element can be any kind of plasticity you want to implement. But the damping here is something that Cedric will talk about more in the last part of the talk, so I won't go into any detail. And then the final element has lots of different names in the literature. It can either be viscoplastic or thermoviscous or a Kelvin element. The name really doesn't matter. Essentially, it's just a spring in parallel with a damper. And again, the damper does very much the same as what Cedric will be explaining with the viscoplastic element. It just stabilizes the entire element so that you don't get very fast strain rates. Then all of those 5 real, in inverted commas, deformation mechanisms are then put in parallel with a very simple viscous element. So this is another viscous damper. And this damper essentially just limits the strain rate. So it essentially gives you a minimum viscosity. And then finally, that entire bundle is put in series with another viscous element, and this viscous element is extremely stiff, and that just controls the maximum viscosity. So all of those components together give you what we have planned for our composite rheology. If you have more different rheologies that you want to put in, the way in which we've implemented this, it's essentially plug and play. So in the code, if you want to add another individual rheology mechanism to the composite rheology, then it's about 10 lines of code to get that done completely. So it's no particular work for the user. Okay, so to move on to the next slide, our action plan, and these are going to be the last two slides from me. The first point is that really our intention is to allow the user to plug and play different creep mechanisms and to turn off different mechanisms when they don't want to use it. So you don't have to calculate diffusion creep mechanism, dislocation creep mechanism. If you don't want to use them, we'll just end up having user flags to turn them off. And you'll end up being able to use the same rheological material model without changing your input script very much at all. Of course, within this model, the entire point is that we're trying to implement correct strain partitioning, so that's already implemented. The two things that aren't implemented are damp plasticity. There's a pull request open for that already, and then damped elasticity is waiting on an open pull request before I make my own to add on to the elasticity rheology module. We've already added the soft viscosity limiters, so hopefully that'll improve robustness in evaluations. That is yet to be seen. So if we move on to the last slide. One of the other things that I really want to do with this is to allow different compositional field averaging, so different rock averaging schemes. I said in the first or second slide of my part of the presentation that we were pretty much stuck using isostrain for almost all of the different rheologies that are in the literature. And the reason for that is because we don't do that strain partitioning because it's quite expensive. If we take on that little piece of expense to obtain the total stress, then it actually turns out that it's faster to calculate the isostress rock averaging scheme, which is more reasonable for something like a gneiss, something that has been structured by strain over a long period of time. And by fast, I mean, if you have something like 4 different rock types that you're wanting to average, it'll be 4 times faster because you only have to calculate the stress for the entire composite rather than calculating the stress for every individual rock type. And the last two things that we want to do are to start incorporating the damage into the model, so rheology grain size coupling, and then we want to test with production models to make sure that we are indeed robust to all of the different things that users will throw at it. And at that point, I will leave you with Cedric.
Right. Yeah, so I'm just going to focus here on the part on the plasticity. So I'll just remind everybody that what we're doing is actually we're computing everything in the realm of continuum mechanics. So although we're talking about plasticity and maybe a lot of you actually think of faults, effectively what we need to do is provide a so-called effective viscosity for plastic deformation. And long story short, the formula is here on the screen. Thank you, John. Eta P is, that's the effective plastic viscosity, and effectively it's the yield stress, which can depend on pressure and other variables, divided by 2 times the strain rate, and usually it's the second invariant of the tensor, so it's a scalar. Right, and the equivalent diagram is shown on the right here. Okay, the thing is, in areas where, for instance, little deformation occurs, or if you have a very linear flow, then you might have the case that the strain rate goes to 0 or becomes very, very small. Looking at the equation, it becomes very clear that your effective viscosity then explodes, becomes infinite if you want. On the other hand, what happens is that if your strain rate becomes very large, so you are a very high degree of localization, whatever the reason may be, then your viscosity goes effectively to 0 or to very, very low values. So purely numerically speaking, this is a big problem because our solvers are very sensitive to viscosity ratios in and viscosity gradients also in the domain. More specific to aspect has adaptive mesh refinement, right? And if I decide to approximate the strain rate by being the variation of velocity over a cell of size h, every time that I refine my grid, h becomes smaller, and so my there should have been decreases there. Strain rate increases, it yields a lower viscosity, which yields to more localization, which yields higher strain rates and therefore lower viscosity, et cetera, et cetera. So we might have a case that if you tune your AMR to the strain rate field, you might have a runaway effect, as in you will want to keep refining and refining. Of course, there is a limiter on how much refinement you do in the code, but effectively, you might enter a runaway effect, and maybe at some point your mesh becomes too large and you might experience a crash. So these are two big problems. And the usual quote unquote solution is to actually implement viscosity cutoffs. And these are numerical and physical parameters. I mean, obviously we have an idea of acceptable values of viscosities in lithospheric domains or mantle convection problems. So we have a minimum and a maximum viscosity that the user may choose. But the thing is, the real problem, the underlying problem, is that there is no inherent length scale in the plasticity model. Next. Thanks. Right. And so as Bob described, one solution is to actually put a viscous damper in parallel with the plastic element. And then if you do the calculations, you see that the effective viscosity is the same formula as before, but there is this plus eta m. And you see right away that if your strain rate now becomes infinite, so very large, then your viscosity no more goes to 0, but actually goes to eta m. So effectively, your additional damper is a viscosity limiter. And it applies only to the plastic bit, right? There is another viscosity limiter like Bob showed for the whole assembly, but this one is specific to the plastic bit. So the thing is, we have mesh independent minimum viscosity, right? And if you let AMR loose, then you will not have this runaway effect, because at some point, no matter how large your strain rate becomes, then you will hit the additional damper viscosity value. So that is neat. Of course, the question remains, okay, how do I choose my eta m value? That is a reasonable question to ask. And there is actually a benchmarking aspect already implemented. So you have the code name here. And these IDs are actually have been published recently by Duretz et al. And René de Borst and his collaborators. What you have here on the right is actually an excerpt of the hackathon report of last year, where so this is actually I suspect a compression problem where you have this viscous inclusion, the square in the middle. The red bit is actually a viscous layer, and the blue parallel bands are viscous again. And what we do is that we put this through by means of kinematical boundary conditions, and we look at the development of the shear bands stemming from the corners of the square. And what you see on the left is that you have a 32 by 32 without damper result, and you have 4 shear bands. And if you look below, you have the 64 times 64, and you have a different, it looks reasonably similar, but it's not identical shear bands. And especially the shear bands you see for the 64 squared are thinner. If you switch now to the right part of the graph, Well, mission accomplished. What you see is that aside from a few little pixels here and there, what we have is is conjugated sets of shear bands, which are, at least in the eyeball norm, identical for 32 squared and 64 squared meshes. So that is, this is running in Aspect and in all the codes, but that's just an example if you want of what to expect. Next. And finally, this is not the only way to potentially stabilize the plasticity problem. And this has been explored by Arushi, Juliana, Jonathan, and maybe a few others during the hackathon. And the other idea is actually, I would dare to say, a bit less physical, but nonetheless very interesting and rather cheap as well. So what you do here is that you have this virtually the same formula as the case without the damper. But if you look closely, you'll see that the epsilon here has a star. And this epsilon dot star, that is the strain rate field that results from actually a diffusive process. So what we do here in this case is we take the velocity field, we compute from it the strain rate field, but before we use it in the rheology, we would actually literally diffuse it, like think about diffusing a temperature or something like that. And the value of the diffusion coefficient, which is not trivial to choose, actually introduces a length scale. And that is exemplified here on this figure at the bottom, also from the hackathon report. What you see from left to right, you have an increase of resolution on the same problem. And what you see is that with increasing resolution, the shear bands become smaller and smaller. And on the bottom, it's the result, albeit in a different color scale, it's the same field, but now with this diffusion process implemented. And you see that from 1616 to 128, 128, we virtually end up with the same strain rate field. So we have also stabilized, we don't have this runaway effect in terms of shear band thickness. And I believe this is all I wanted to say, right? There is, yeah. John?
Yep. So just to wrap up, a few quick points, and then we can go into questions and potentially do sort of an interactive sort of pass through the code. So, but then Aspect, it currently has the ability to simulate a wide range of nonlinear tectonic processes for incompressible viscoelastic plastic deformation. As Bob and Cedric described, there's a lot of work going on for new formulations for doing different methods of compositing these different deformation mechanisms, and then also these new plasticity stabilization schemes. And so then that's all ongoing work. And then over the next year, we're going to be adding new examples, updates to the manual and cookbooks to the repository, and also hopefully writing some of this up for publication. But then in terms of over the short term, the main things we're going to be working on in adding new features to the code is then compositing with the elastic deformation, then hopefully compressible elastic and viscous deformation incorporated into the viscoplastic material model. Certainly we're going to start with viscous first. The compressible elasticity is probably a bit of a longer term project. As Anne and Esther are going to talk about later today, they are working on rate straight friction formulations. And then sort of the bigger longer term item, although it is work in progress now, is incorporating into the viscoplastic material model or other material models, the two-phase fluid transport, and then hydrofracturing, so modifying the yield criterion to include fluid pressure, and then fluid rock interactions. All this is in the pipeline. So thanks, and we'd be happy to take any questions, and if people are interested, do a deep dive through the code. Thank you.
Thank you, John. So we have about 10 minutes now to talk about these topics, to answer a question or to take a look at what is already implemented. So feel free to unmute yourself, ask a question if you would like to hear more about any of these topics.
I have a question, which is, are a lot of these, for example, I'm working with something that John gave me, and there's the stresses on particles. So is a lot of the material model, the basic stress and strain fields on particles, or how are you, or are they on composite fields, or are they
Yes, and so that's a good question. So then so then the only case where we need to track stresses right now is for viscoelasticity. So that's the only case where we're actually advecting and tracking stresses through time. And so then the way that works actually now is that, so then we originally did that on compositional fields. It was basically done in the material model, or actually in a rheology module through reaction terms. But now what we did is that's implemented on particles is what it's implemented for particles as well. But what we do in the particle section of the code is we actually call the rheology module. And so then, so then that basically allows not duplicating rewriting code to do the same thing for calculating the elastic stresses. So basically, in the future, anytime we want to track stresses and advect them through time, we would hopefully call the rheology modules, which are explicitly computing those stresses. Does that answer the question, Gary?
Yeah, one follow on. Does that mean that the particles actually are, once you compute the stresses, you're putting them back onto the particles, so they're changing their values as they move, unlike a lot of the models we use, you have a fixed density or viscosity or whatever, and it never changes. It just advects passively with the flow. But are you changing the stresses as you go?
Yes, exactly. So then for elasticity, at least, in the model, the stresses are always changing, but in terms of, and so for viscoelasticity, that's the only case where we actually need to track it through time and advect them explicitly. And so there at each time, so I'm actually, so they're actually in each nonlinear iteration, we are doing the updates. And so the values on the particles are actually being updated. And the way that works is, so the particles have the particles have the material model, the values needed for the material model input. So then you can access the pressure, temperature, strain rate, and velocity through the particles. And then through the particle interface, we would pass those values to the rheology module. And then the values calculated in the rheology module will then be stored on the particles and then eventually advected.
So I'm sorry, one more question, which is that all the damping and the models you have for limiting, which aren't on the particles, does that mean that for all intents and purposes, you don't have to worry about limiting on the particles because it's being done in the rheology model for things like stresses and stuff like that?
Yes.
Thank you.
Yep.
I think this is pretty cool. I think you three have been, or 4 or 5 or however many actually contributed to this, have been doing just fantastic work. This is more a question for my own understanding. So I get that all of the effects that show up in this analog model that I think Bob showed are physically motivated, but how much can you really say about whether it makes sense to have them linearly arranged as opposed to parallelly arranged? I'm trying to understand this sort of from a microscopic scale, right? And whether you have to take the arithmetic average or the harmonic average depends on whether the deformation is parallel or perpendicular to crystal planes, for example, right? And or let's say if you think about it as a layered material, how much can you really say whether that arrangement is physically correct or not correct?
Bob?
Yeah, good question. I don't think there is any correct model. So at the grain size, you're going to be a lot of your creep is going to be isolated at grain boundaries. You're also going to have dislocation creating new grain boundaries. The structure of those dislocations can really be quite complex, whether you have dislocation glide and climb or other forms of dislocation creep. There is so much complexity in there that I'm not sure I can give you a satisfactory yes or no, and this is what we should definitely do. In terms of compositing your different rock types. So let's say at the mesoscale, or at least on the thin section kind of scale, if we ignore what is going on inside every single grain, and we instead look at, okay, we've got this garnet mica schist, then what's happening? I think you can say that isostress is going to be a more reasonable approximation to rocks with a very strong texture. Simply because we can see in thin sections that we are, most of our strain is going on in our weak phases. And at that point, I guess, if you want to include things like that, then you're going to have to use the new scheme that we have. Which one is more accurate for different situations, I don't know. But there are certain cases where we can definitely say, well, this is a better approximation.
I mean, go ahead.
No, I was just going to say, I hope I answered at least part of your question.
Well, so this is, I mean, this is more a philosophical question that I think I want to ask, right? So you have a relationship of, in the simplest case, viscosity as a function of strain rate and stress, right? And you can write down a very complicated analog diagram and figure out then how would that correspond to a formula? And this formula is going to have a specific form, right? There's going to be harmonic and geometric and arithmetic averages, and maybe there's a cutoff somewhere, and maybe additive terms. But it's going to have a lot of unknown parameters that we don't really know, right? I mean, we can measure them maybe on centimeter by centimeter by centimeter scales, but what we really want is scales of hundreds of meters to maybe multiple kilometers. And so I think from a philosophical perspective, couldn't you just say, well, it's a complicated function that I don't have to write down like this with so many parameters, but I could just assume it has sort of this, broad stroke quadratic function, and then there's a cutoff, and I can parameterize the whole same thing with just 3 parameters. It has no physical meaning anymore, right? It's not. It's sort of just a crude approximation for a function with a specific form with many parameters by a function with a generic form with few parameters.
I feel that that's what people. I mean, that's what we all do. Our true form. If we want to have something that completely obeys experiments, if we assume that our experiments are completely error-free, which they most certainly are not, then we're going to have to use hundreds of parameters, and we're going to have to look at much more physical parameters than the ones that we use in our rheological expressions. So diffusion, dislocation creep, Pearl's law creep, fundamentally, they're just Arrhenius laws with certain powers applied to them. They're nothing. They have physical justification, but they're not physical laws by themselves. So I guess the question then is, well, how much complexity do we need to add to our models to get the behavior that we want? So the way in which the equation of state side, certainly the models that I've used, and the ones that Juliana and Rene are hopefully going to publish soon, we use lookup tables for thermodynamics. We could do exactly the same thing, at least for diffusion, dislocation creep, Pearl's law creep, for rheology. We could just use a lookup. It would have a relatively simple form. We could fit it with some splines, and it would be really quite accurate. I guess the question is, do users want something like that?
I mean, is this something that people have done, that where you say, well, I have this really complicated analog model here, and I'm putting in reasonably physical or physically motivated values for all of the parameters, and then I'm going to just create a 2-dimensional plot: strain rate, stress, viscosity, right? And you're going to get some sort of surface, and I'd be quite curious how that surface actually looks like, right? Is it is it complicated? Does it have lots of different facets? Or is it something that you could, in principle, parameterize with just 3 or 4 independent variables that you could actually have a hope of maybe identifying, or we say it's as good as this complicated thing, but it's I can compute it faster by a factor of 100 or something like that.
So in terms of how anyone made the plots, there are Ashby plots, which are essentially what you're describing. So deformation maps are pretty common within the mineral physics, the mineral physics community. In terms of finding a simple parameterization, again, people do this by imposing piecewise linear or piecewise planar functions. And that's essentially what John already has in the viscoplastic module. You just say, okay, we've got diffusion creep here, we've got dislocation creep there, and we have a turnoff at a certain stress. And that's pretty good. That's not bad at all. One of the reasons why I wanted to implement this composite is that I've had several discussions like this where we discuss, well, do we need it? This quick approximation is fine. It's fine because everyone's used it, therefore it's fine. And there's a bit of, well, has anyone tried to do the complicated, slower thing to see whether we need to worry? And so that's one of the things that I want to do. And if it turns out we don't need to worry, then we don't need to worry. But we then have that model there where we can do direct comparisons.
I mean,
yeah,
sorry, John, just a sec. I totally think that you should, right? I'm not trying to talk you out of it. I'm just trying to understand, like, how much do you actually gain, and how complicated are these surfaces? And so I spent maybe more time than I should have with neural networks over the last year, and they're of course meant to learn exactly these sort of complicated, expensive surfaces, right? And now I'm intrigued, and I'm thinking, well, maybe we could learn this surface and make a much cheaper model out of it. Anyway, John.
I don't want to cut off the discussion, John. Do you have something quick, or time-wise we need to move on? And we have a few short talks that also go into the direction of rheology and crystal structure. So maybe we can revisit the topic after the short talks in the discussion part today. Does that sound good?
Yep.
Okay.
Sounds good.
Awesome. So then thanks for this discussion and for the keynote. And we'll move on to the next session with short talks.